Tonight's pre-talk speaker, our student speaker, is George Abraham, third year astrophysics and geology student, talking about, and I'm going to get this wrong, the geomagnetic field.
Yes.
That'll do,
exactly.
Close enough.
Yeah.
So with no further ado, a nice warm keel welcome to George.
Cool, so I thought I'd just quickly start off with not a title slide, but this will be a video here you might recognise. It's something from, it's a video from the ISS, and it's of the Aurora. It's actually the Aurora Borealis. This is it flying over Europe. So very, very pretty there, and that's to introduce the topic of, if I can, there we go, the geomagnetic field. So this is something I'm quite interested in because it feels very simplistic to start with, but actually it's very complicated. It's very complex. It's made of different layers. So before the world of satellites, and indeed now, but especially before all the satellites, we use a lot of these. These are planes with this thing at the end. Which is this magnetometer, and that's how we detect the magnetic field of the Earth for things like to understand what's happening underneath the Earth. These different sources of magnetic field. Now this is more for local sources. So for my dissertation. These are some figures that are probably, there's some mistake in there, but you know, I thought I'd show them because it's cool. So on the left. You can see, so these planes, they fly in a grid pattern. So you might just be able to make out there's these dots that are in a grid. This is actually the Isle of Mull. You might just be able to make out an OS map underneath all these dots. Yeah, so they fly in grids. And then what you have to do is you actually have to then grid the data so that it's in a nice format. So it looks a bit. You can understand it a bit better, as it were. And then what you have to do is you might just be able to make out this says reduced to the pole. What does that mean, and why on earth do you need to do it? Well, basically, the magnetic field is it's not just a vertical thing. It's a dynamic thing. It changes, and it's also a vector. So it's at different angles at different places. So at Mull, we've actually got what's called remnant magnetisation, which means that it's that when the magnetisation was baked into the rocks, it was actually the opposite way around. So the way around it is today, which I'll show you in just a sec why that is. But this is just a nice little diagram here. This is a model of it's quite an old model of the Earth's magnetic field, and you can see here how crazy it is, especially in the middle, and how it is in different directions as well. So the orange here means the field lines are pointing away, and then the blue is going into the Earth. And then, so in terms of field sources, you might immediately think about the core. As the source of the Earth's magnetic field. Well, it's not that simple, which makes it very difficult to predict. So there's just to introduce all the different sources, which I'll very quickly go through. We've got the fluid core here. We've got the mantle as well. We've got the crust, the ocean, and then the ionosphere, which is just the bit here. Here even, and then the magnetosphere. And you can see in each of these sections, there are these circles. This is supposed to represent currents. And in fact, I've got this lovely equation here. You might recognise it. Well, J here is the current density vector. You've got sigma, which is the conduction, or the conductivity. E is the electric field, and then V, that's the velocity vector, and B is the magnetic field vector. Basically, what this is saying is that when you move something, so when you move when you move something through a conductor, it generates it generates these currents. It generates some electric fields, and it also generates some magnetic fields. So that's how we get the magnetic fields in these different places. So thinking about that equation, that's kind of what's behind all of the stuff that I'm about to say. So this is CHAMP. So there's two main satellites. There's actually quite a lot of satellites that have also looked at the magnetic field on a larger scale than that plane that I showed you. But these two are the main ones. So first of all, CHAMP. which is it was a DLR, so a German mission, and it flew at 19,000 to 119,000 kilometers up, and it was basically up there so high so that it could detect the interaction between the magnetic field, the geomagnetic field, I should say, so of Earth and the solar wind. This is a new one. It's still up there. There's actually three. There's so this is called Swarm. There's Swarm Alpha and Charlie, which fly close together, and then Bravo is 90 degrees. So it's like it's that angle away from Alpha and Charlie, and it's like that because it means that they can separate the fields. And in fact, if we combine it with Champ, which is even higher, then you can really start to understand how the fields are separable, and you can understand what different things are contributing to the different parts of the field. So then you can start to predict it. So first of all, we've got the outer core. I'll start with. It's not a journey into the Earth. It's a journey from the centre of the Earth. So if I just play this video, so here what you're seeing is a model. Nanotesla is what we use as the unit of measurement for magnetic fields. So blue is negative, orange is positive, and then you've got density, which is the core density, and you can watch this fluid as it flows out, and then watch what happens here. So this is time there, and then there we go. So what you're seeing here, so it says jerk. This is basically the change in acceleration. So the acceleration is greater as shown here. So basically, what it's indicating is the magnetic field is changing because of density of stuff moving in the core. So this is how the magnetic field is being generated in the core. The temperature gradient is from 3,500 degrees C to 5,700 degrees C. So this creates a big heat flux and creates this massive jet stream within the outer core. This jet stream is about 3 times the speed of normal flow, which is 50 kilometers per year. So it's very fast in there because it's around the viscosity of water. So it's almost like a coffee cup. In a way, you might want to think about it. And then another effects that they found are these two blobs. Because one blob in the core got bigger than the other blob, it's actually been it's accelerating the North Pole towards the bigger blob. And so between 1990 and 2005, it was about 0 to 15 kilometers per year. The North Pole was moving, but now, so in 2019, it's 50 to 60 kilometers per year. So it's been accelerating, and this is the reason why that they think that it's doing that. And it's really important, all this stuff, because we need to know where the North Pole is, because otherwise your phones aren't going to work. It's a very important thing. So things like GPS, phone technology, important in modern life. Another thing I talked about before, the lithosphere. So that's the crust, basically. This is called the LCS1 model. It uses Swarm, Alpha, and Charlie alongside Champ to separate the magnetic field and understand and see specifically the lithosphere produced. And you can see one of the things that's important with this is that, as I said before, because the magnetic field flips, the remnant magnetic field, so the magnetic field at the time of when it was erupted, as it were, is baked into the rock, and you can see that in these. I mean, you can't see it, it's so small, but you can. It is there, and it does contribute. But also, what other things that contribute, because remember the sigma in that equation, the conductivity. So conductivity is a function of composition, temperature, water content of the rock. So you can tell something about the geology of the rock from this magnetic field, from this diagram, which is very cool. But note here, only 3% of the magnetic field is produced by the lithosphere, whereas the other one, I didn't say before, but 94%. Was produced. Another weird thing that you might not think about is the ocean. Look at this video here. So this is again pink is high magnetization, blue is negative, And you can see how dynamic it is, how it changes. This is actually over one tide. It's the biggest tide. It's called the M2 tide, and it's a 12-hour tide. And so tides, obviously, they move lots of water, and water is salty. And salty water is conductive, as you should know, because you shouldn't take a bath with electricity. This means that it generates these magnetic fields, and actually you can use this oceanic magnetic fields to study the thermal flow in 3D in the oceans, and B also to understand what's below the oceans, the mantle and the crust, because of the fact that current flows. There is some conduction between the oceans and the crust and the mantle. So you can understand what's happening there as well because of these currents. So another really interesting constituent. Another one, the ionosphere. I pointed out before. Sounds a bit the ionosphere, but it's very cool. It's got these thermal winds. So here, this is in meters per second. The velocity of the thermal wind, and then these lines represent magnetic field lines, and this here, so this is the mean drift velocity of plasma. So plasma, when I say plasma, I just mean like ionized particles, so electrons, positrons, lots of charge, lots of energy there, and you can see. So this is the mean velocity, and then it's a high velocity, and then it goes to a negative velocity. And because of this, what it's demonstrating here is movement of charged particles because of thermal wind generating a magnetic field. So the magnetic field is being produced by weather or by movement of air. It's very so another source there that you might not have expected. Here it's a very complex diagram, so take a moment. But this is showing plasma, but plasma from the sun. So this is another thing that affects our magnetic fields. This is the magnetosphere. It's the outer part. These lines here are lines of magnetic fields, and when the magnetic fields, when these lines join together, they snap and they accelerate particles. They accelerate charged particles, and what it's showing here is that the plasma that's being thrown at the magnetosphere is deforming it, and it's deforming it in such a way that it flattens at the day side and arches out at the night side. So you've got to understand all these different layers. So from how the solar wind interacts with the outer layers of Earth, to how the outer core, the dynamics of the outer core, to then understand the entire thing. So it's a very complex system. And these complex systems aren't just based on Earth, they're also based across the solar system, across the universe, and we've been able to send some probes out to have a look and see what's happening. Now, this is a future mission. It's something that's going to happen very soon. You might have heard of it. It's called I should have looked this up. I think it's called Psyche. Or Psyche. Yeah, I'm going to say that. Apologies if I'm wrong. But anyway, this is an asteroid. It's the largest metal-rich body in the solar system, or iron-rich body, I should say. And so I should note that all planets, apart from Venus and Mars, have a magnetic field. In fact, Mars did until its core stopped flowing. And we think that maybe Psyche might do, but the reason is because so if we find a magnetic field, it could indicate that it was part of a core, and then it had this magnetic field baked into it when it was in a liquid state. Whereas if it doesn't, then it could indicate that it's formed of primordial unmelted material. So depending on the magnetic field that we see, depends on the structure within this asteroid. It depends on its history. So that's why we're sending a probe here with a magnetometer to measure this magnetic field and understand what's happening. This is what we're sending. It's called the Psyche Flight System. Very inventive, but this figure here is actually showing how the magnetic field or how magnetic fields are generated around the spacecraft, because you don't really want those interacting with your measurements. And in fact, we saw on the very first image that that plane that had a beam, or had a boom at the end, which had the magnetometer on it, and it was away from the plane because we don't want currents inducing magnetic fields and us measuring that. So again, here we've done the same thing. We've put the magnetometers on booms, but we still can't limit all the currents. So what they've done is actually models. This is a model of the magnetic fields produced by currents flowing, and then you can kind of work out what's being produced by the spacecraft and what is actually the asteroid. But it's a very complex operation to not only understand the magnetic fields, but then to actually measure them. So there you go. So yeah, and that is my very brief zip through from the Earth to our solar system. These are my references, and thank you. If you does anyone have any questions?